So today's lecture, we're going to focus on thinking about solving for hydraulic conductivity and transmissivity in confined systems under steady state conditions. So, we've talked a lot about how important it is for us to understand what aquifer properties are. And the reason it's so incredibly important to understand what they are is so that we can understand things like the amount of drawdown that might take place in an environment. So then we're also going to take kind of what might be a back of the envelope calculation, which is estimating transmissivity from specific capacity, right? Another new term, so that it might be something that you calculate in the field to get just kind of your hands on what the transmissivity of an aquifer system might be. It's kind of a double check when you're thinking about it. All right, so pump tests and well hydraulics. We're always in search of estimating hydraulic conductivity, and especially in the field, because as you saw, we can have these small permeameter tests, but our systems are much more heterogeneous than small permeameter tests that we did in the lab. So we have changes, what we're looking for are changes in water levels, and these are observed either at the well, as well as observed at wells that are nearby. So we're going to have something that's measuring water levels in the well, right, as we're pumping or we're enacting different kinds of changes in water levels. And then oftentimes we're going to have water wells, observation wells is what we're going to call them, nearby, so that we can understand how that change in the driving well or the pumping well or the injection well are influencing the area around it. And then we use these observations to actually estimate that hydraulic conductivity, or we may multiply that by our aquifer thickness. And remember, that will get us back to our transmissivity. So we can think of this as the inverse method to the groundwater flow equation. So instead of trying to solve for the heads, we're trying to estimate for K because we know what the heads are under different conditions under different times. So when we think about aquifer, water storage in an aquifer, we can recall that we always have our inputs minus our outputs, which equal our change in storage. And if we say we're at steady state, right, then we have our inputs equal our outputs. And we can think about this be staying the same and under these conditions. Now, if our change in storage doesn't equal 0, then we would say that H is changing over time. So let's go ahead, and it's a good idea to maybe even draw a cross section like this to think about how we look at doing these kinds of aquifer tests. So oftentimes we have something that's pumping. There are times where we actually do injections as well, but we can think of it right now as pumping. And we know that when we pump, right, we can draw the water level down, and that we can think about that drawdown more or less as being a circle around the well, right? So we could think of these as kind of the potentiometric surfaces that might be created around the well, and that there's a radial influence surrounding that well as you pull water in. Right, this is a simplification, but that's the idea. And so when we have drawdown, we have our cone of depression. We have the proportion of drawdown that's right here. So let's kind of annotate these a little so you can see them. So our cone of depression may be going from here to here, right? As soon as it's kind of lower down in terms of the radius here from the initial condition. Then we have the actual drawdown, right, which is the change in the head from that initial condition as well in this system. And so we can have observation wells. So this is an observation well, and then here is our pumping well. And we can have information about the radius between those, right? So where are we measuring the drawdown here compared to the drawdown in the well, and the radius and difference between those. And so then we can start to think about, well, what is the actual storativity of the aquifer, right? And then what is maybe the transmissivity of that aquifer? So when we're thinking about pump tests and well hydraulics, there's two directions that we can go. So the first direction we can go is what we call as pump tests. So what happens in a pump test is you pump a well, right? And you usually keep it at a constant rate. So you try to maintain a constant discharge that's happening from here, and you observe how the head changes, right? Now, eventually, if your aquifer is plentiful, you will create a drawdown and a cone of depression that remain at kind of a steady state condition. So when we're doing these types of tests, we are relying on the idea of having observation wells in this system, right? Along with the actual pumping well itself. And we're relying on observing the drawdown that's in that system. Another type of test, which we're going to go over later in a couple of lectures, is thinking about slug tests, which is a much quicker change in head, which is observed at the same well, right? So it would only be observed at the well where we're changing the actual inputs or outputs to the system. So at this well in that instance. So here's another way of thinking about it. Sometimes it's important for us to get multiple kinds of viewpoints. This one's from your book. Sorry about that. So we'll have like what might here be called the production well or the pumping well. And then we have observation wells. So we may have one observation well here. We may have a second one here, right? And then back here is our head level at the initial condition, just to give you an idea of what these look like. And sometimes you'll see the small s with located here. And all that means is actually the drawdown. So what was the initial condition minus where the water level is now? Again, here, it could be what the initial condition was minus what the water level is now here. And that's what they call the drawdown, or oftentimes S. So the first of these equations that we're going to work with and solutions that we're going to work with is something that's called the Thiem equation. And it was developed in 1906, so it's been around for quite a while. And it relies on a couple of assumptions. So we have a steady state condition. So there are no changes in head. So we've drawn it down, we've pumped it up, and now the system is essentially at equilibrium. And we can say now there's no change that's taking place in the heads as we begin to make our calculations. We're also going to say that the system is homogeneous. And we're going to say that it's isotropic as well. And that the well is fully screened, and meaning that it's fully penetrating. So the screen is going over the entire unit of the aquifer thickness itself. So the way that this works is that we can consider Darcy's law through a cylinder. Now I'm going to show you a number of equations right now, just to demonstrate how this equation was derived, but I'm not expecting you to be able to derive the equation itself. So remember, when we think about Darcy's law, we always had a large flux here, our discharge here, Q. We had our hydraulic conductivity. We had some gradient in the system. And then and so this gradient here is just the change in head over the radius, right? So the radius in any given direction is going to be the same because we're solving for a cylinder in this environment. And then we're going to say, what is the radius, right? Times pi times 2, right? So that's going to give us an area in the system times our overall thickness of the environment. So we can rearrange and we can integrate this same equation as you see here. And we can end up with that the change in our head between well 2 and well 1 is equal to our 2 pi times our hydraulic conductivity times our thickness divided by our radius at the second well over our radius at the first well, and the natural log of that system. So then we can derive what's called the Thiem equation because we're interested in understanding transmissivity. Now remember, if we take K and we multiply it by B, we have our transmissivity. So we could put T in here. So remember, this just equals T, right? K times B equals T. And we can rearrange our equation, and the Thiem equation, which solves for transmissivity in this system, is equal to our discharge times 2 pi multiplied by our change in head, or our head level, sorry, at H2 and H1, multiplied by the natural log of our radius at the first location and our radius at the second location. So here, when we're solving for the Thiem equation, right, if, for example, if we're using meters, we need to be consistent with our units across here. So meters, and if we're using seconds, then we need to be consistent about using those. But otherwise, it's standing in typical SI units, right, you can plug those in and be able to solve the equation. And you can use any two observation wells that you'd like. Now, sometimes for those folks who might be going off and interacting with the USGS, sometimes there's what's called USGS units, right? And there is some kind of conversion between our standard units and USGS units here, where our Q might be in gallons per minute and our T might be in gallons per day, per foot, and our radius and our height, our changes in head levels are in feet. Now, if you see it in this USGS conversion or USGS units, right, just remember that you have to alter the equation just slightly to account for these changes in gallons per minute, gallons per foot per day, gallons per day over feet, and then feet. And you'll see this for a couple of different types of equations that there might be a slightly different usage when it comes to a group like the USGS. So another way, and when you're in the field and you're thinking about an environment, another way to think about our transmissivity and getting an estimate and asking ourselves as we move through, how, like, it kind of gives us just some conditions to think about. We can actually use what's called the specific capacity to be able to estimate the transmissivity. Now, the specific capacity is just the ratio of the pumping to the ratio that has been drawn down, right? And so again, that drawdown is S, and S can be the head at the initial condition, right? Minus and the head at the condition that is in at some time in the future, right? Once we've created the drawdown in that system. So we can say again here, we have that specific capacity. It's the pumping minus your drawdown at a given well. And we can say this is, okay, if a well is pumped to approximately equilibrium, right? So we're basically at the same conditions as the Thiem equation that we were just talking about before. We can also say a good well would be able to produce about 50 gallons per minute per foot of drawdown, or about 20 feet of drawdown at 1,000 gallons per minute. So, just trying to give ourselves some estimates of what this looks like. Now, when we begin to use this equation to estimate our specific capacity down here, our specific capacity then is going to be set equal to our volume of discharge or pumping, right, over this kind of change in our heads. Now, when we say E is corresponding to an effective, where you would move to where you'd have an effective drawdown of 0. So what is your head level at an effective drawdown of 0? And that means you're moving far enough away from where the pumping has taken place that pumping is not impacting the water levels in that system. And same with that radius of that environment as well, right? So where the drawdown is effectively 0 is some distance away from the actual pumping well. And then we can have the well itself, and we can have the head level and the radius of the well itself where we're pumping in that environment too. So we can say that our volume of water is just going to be equal to our transmissivity times 2 pi and that we can equate this change in drawdown that we have here to the natural log of how far away it is you have to go to effectively have your water table not affected by pumping, and then the water level that's at the well. Now, again, what we can say about this is, generally speaking, our rules of thumb is transmissivity is about 1.25 times your specific capacity. And the reason we can say that it's about 1.25 times your specific capacity is because this ratio, right, of our natural log is fairly insensitive to changes in the ratio itself. So we could say, for this instance, if we have a well, right, that has a radius of 6 inches, and that we have our effective radius where we no longer see pumping is either 500 or 5,000 feet away, we can essentially say that our effective radius is either, in the first instance, 1,000 times the distance of our well radius, or we can say it's 10,000 times the distance of our effective well radius, or our well radius, right, is our effective radius here. And if we were to take, right, basically either the log or the natural log, right, which is in the system, we would end up with values of 6.9 or 9.2, right? So this value here would represent here if we were using just 500 feet, and this value here would represent, again, this value up here if we're using 5,000 feet. And then when we plug those in, right, and we say, okay, let's plug these in, and we divide by 2 pi in terms of this value, right? So taking this value here, dividing it by 2 pi, what we find out is that the specific capacity, right, under this condition is 1.1 times your specific capacity and equals your transmissivity, or 1.5 times your specific capacity. So we're not even changing necessarily an order of magnitude, the value of transmissivity, which is often why we say somewhere in between about 1.25 is not too far bad of a guess, right, to multiply your specific capacity to get a value of transmissivity. Right? Not the best value of transmissivity, but it's a back of the envelope calculation that you can do to kind of check yourself and say, okay, well, generally speaking, this is what I would think the transmissivity should be near. So specific capacity, remember, is not the same as a storage parameter. It is not specific yield. It is just the volume of pumping, right, as opposed to the change in actual storage of the system. So that's an important factor to keep in mind. And the other thing that you need to kind of keep in the back of your head is that if there are frictional losses attributed to the well, the value of this T that you might calculate just from the well itself may be lower than the actual T that represents the aquifer system. So those frictional losses can be attributed to the fact that you have differences in your screen intervals, right? That you have packing material or filter packs that are surrounding your wells that can be creating some of these frictional losses, right? By just using the direct observational well for this calculation, which is why we use, instead of just using that pumping well, right? We'll use several different observation wells in there to be able to make these calculations. So that's why we rely on things like the Thiem equation or equations that we're going to look at in the future as well. All right, thanks.